So Joule's experiment established that work and heat are equivalent. This means work can be converted into can be converted into work, can be converted into heat. Okay, so this means if we throw if we drop so an object, very big object, this is the object. Okay, so say suppose this is a very high. Okay, if this object falls down here, say after some time it will be at the ground level, the same object. So after falling the temperature of the object should increase. Okay, so this can be noticed only if the object is held at a very high object, at a very high place. So height should be bigger. Okay, so this means in this scenario gravitational potential energy finally change into heat energy. So it still follows the principle of conservation of energy. So we define the two unit of heat. One is joule, other is calorie. So they are related by 4.2 joule equals 1 calorie. Okay, so they are both the unit of work and heat. Okay, so how they define? So definition is as follows. Say, for example, you have to take a mass of this object is 1 gram. Okay, say, for example, its initial temperature is 14.5 degrees Celsius and its final temperature is just changed by 1 degree Celsius, so it will be 15.5 degrees Celsius. So you see that change in temperature is 15.5 minus 14.5, so basically 1 degree Celsius. So in this scenario, mass is 1 gram and temperature change is 1 degree Celsius. So the amount of heat required to reach 1 gram water to reach the temperature of 1 gram water by 1 degree Celsius. Okay, under this condition is this: you must have water, temperature change must be 1 degree Celsius, and mass must be 1 gram. In that case, this amount of heat supplied that we supply is called 1 calorie. Okay, so that's how we define the calorie. Calorie is amount of heat required to raise the temperature of 1 gram water by 1 degree Celsius. Next, we'll go to the specific heat capacity. So we define a specific heat capacity is amount of heat required to raise the temperature of unit mass or substance by 1 degree Celsius. Okay, so this means we have to define the substance, then the temperature change will be 1 degree Celsius and mass should be 1 gram. Okay, so for example, say we have this mass is 1 kilogram. Okay, this is the mass. Say its initial temperature is, we can write T1, okay, then we are supplying the heat. We're supplying the heat. Then say its final temperature is equals T2. Then you can write change in temperature as delta T equals T2 minus T1. Okay, so we define a specific heat capacity. We generally represent by symbol C depending on textbook. So a specific capacity is amount of heat supplied is Q per unit mass per degree per unit change in temperature. So this is the standard definition of a specific capacity. So you can check the unit. Joule, Q is measured in joule, M is kilogram, so per kilogram per degree Celsius. Okay, so in this equation, what I have introduced here, this C is the specific heat capacity. Okay, so this Q is the mass. Q is the heat supplied. Okay, M mass, and this delta T, this is the change in temperature. Okay, so we can write this equation as Q equals M C delta T. This is the heat gained or heat lost formula. Okay, so if you measure the mass in mole, then we also can be written as N C change in temperature. So in this case, mass is measured in mole, number of mole. Okay, C, now in this case, this is called the, because mass is measured in mole, so it's called molar specific heat capacity, because we measured it in mole. Okay, so this is the definition, how it works. One important concept, I will say that this is different for different parties. So it is different for each material. This will be not same. So copper has different specific heat, iron has different specific heat. Water has different specific heat. So different substances will have the different specific heat. Okay. So for example, if I say in the case of water, the water has a specific heat capacity is 4200 joule per kilogram per degree Celsius. This is the specific heat capacity of water. Okay, so what does it mean? This means this is the water. Okay, so mass of water must be 1 kilogram. Okay, then we must have to supply the heat. Then heat supplied, this Q must be 4200 joule. Okay, this means, say, before heating, temperature T1 is, say, for example, 28 degrees Celsius. Okay, so after heating, after supplying heat, of 4200 joule, your temperature, final temperature T2 will be, say, should be increased by 1 degree Celsius. So it will be 29 degrees Celsius. So delta T, with the change in temperature, is T2 minus T1 is 1 degree Celsius. Okay. So this means a specific capacity of water 4200 joule means 4200 joule of heat is required to raise the temperature of 1 kilogram of water by 1 degree Celsius. Okay, so this is the definition of the specific heat capacity. Okay. Next, we'll go to the specific latent heat capacity. Okay, specific. So we generally use a specific to indicate the term of one. So is the latent heat. So you know, latent means hidden. So let's start with an example so that we can start with. So for example, in general, what will happen if heat is supplied to a system? Okay, applied to a system, two things could happen. One could be change in temperature. Other is change of state. What in state means from solid to liquid, liquid to gas, it could change like this. Okay, so let's start with one example. Say I have ice of, so I have ice at minus 10 degrees Celsius. So this is solid. This is the solid state. Okay. If I heat, what will happen? If I supply the heat, it will not instantly convert it to water. At first, it still is ice, but temperature will increase from minus 10 to temperature is degrees Celsius, 0 degrees Celsius. So still ice is solid. Okay. If you continue heating, what will happen? Now ice converted to water. Now there is a change of state. This is converted to liquid. But be sure that in that time, temperature will not change. Temperature is still 0 degree. Okay. So when change of state happens, in that scenario, no temperature change. You see that. Okay. So if you continue heating, what will happen? Say it could go, temperature increases 1 degree, 2 degree, 3 degree, say up to 100 degrees Celsius. So it's still water, but temperature increasing means 100 degrees Celsius. So now it is still water. It is in liquid state. Okay. If you continue heating, what will happen is that it converted into vapor or steam, but this is in the gaseous state or the vapor state. So still it could be 100 degrees Celsius. Okay. So here there is two things happened: either change of temperature or change of uh, change of state or change of temperature. Okay. So let's see. So how we can go to define certain term. So you see that at particular temperature, so this is called is temperature is temperature changes from -10 to 0. So 0 has a special meaning because if you heat ice at 0 degree, it converted to 0 degree water. So this temperature 0 degrees Celsius is called the melting point. It's called 0 degrees Celsius. We call it melting point. Melting point or melting point temperature or freezing point. So whatever you say. So this only applies for water. Be careful that, not for every substance. So in this case, it converted from solid to liquid, or it could go from liquid to solid, whatever. Okay. So, but 100 degrees Celsius, this temperature is called the boiling point of water. So this only applies for water, okay? It's not for other substance. Other substance has different melting point and boiling point. Okay, so in this scenario, when it boils, it will go from liquid state to gaseous state. So in this case, the heat, we supply the heat, but temperature actually did not change. So here, when we substance changes state from solid to liquid or liquid to gaseous state, then in that scenario, we call it the specific latent heat. So a specific latent heat is the amount of heat required to change the phase of unit mass of substance. Okay, so for example, so we can go here. So this is not applied here. So water has different scenario. So we cannot write it here. Okay, so we define two terms here, two terms. So when phase change happens, we use the equation as Q equals ml. Okay, so in that case, when phase change, we have Q equals m times L. M is the mass, L is called the specific latent heat, and Q is the heat supplied. Okay, you can put that way. So for example, we can consider a specific latent heat of fusion. Okay, so this is equals to 80 calorie per gram. If you convert to kilograms, it will be, in SI system, it will be 3, maybe 5. We have to do some a little algebra. Joule per kilogram. So what does it mean? If you consider here, to convert 1 gram ice at 0 degrees Celsius to 0 degree water. 80 calorie heat required. Okay, this gives you the meaning of the specific latent heat of fusion of water. Okay, we're just considering water here. Other substance has similar. So this means you have this ice of 1 gram at 0 degrees Celsius. If you supply the heat of 80 calorie, then you know that mass will not change, still 1 gram at 0 degree water. So this is ice melted, right? So this is ice, this is water. So this is about melting point. Let's go about in the case of boiling, because you know that we are mainly interested where change of state happens but not change of temperature. Okay, so let's go to the change of state scenario. So for the water, latent heat of vaporization is for water is 334 calorie per gram. Okay, so what does it mean? If we have this in a container, say we have water. Okay, so this is 100 degrees Celsius water. If we continue supply heat, if we supply the heat, okay, then it's converted to steam. At same temperature, 100 degrees Celsius. So amount of heat required is 334 calorie. Okay, so if you convert it to SI system, it will be 226 1 2 1 2 3 4 joule per kilogram. Okay, this is not need to remember this quantity will be given. So this means you have to put water. We need just 1 gram. Okay, so this gives you the idea that 334 calorie heat is required. Heat is required to convert 1 gram water at 100 degrees Celsius to 100 degrees Celsius steam. Okay, so this is how we talk about the specific latent heat. So again, repeating is this: we use the formula Q equals mc theta, or change in temperature. This is for change of temperature. Okay, Q equals ml. This will be applied only if we have change of state. Let's go back. So this will be ml. So this will be for change of state. So in heat, in this topic calorimetry, we use these two equations to have a change of temperature or change of state. So this is just a plot. They give you the temperature along the axis y, and amount of heat is supplied per unit mass along the x-axis. So you see that this fat portion, this is the change of phase state. So liquid and steam, water and steam coexist. So this is the water and steam coexist at the same time. So in that portion, ice and water coexist. Okay, so in that portion means, in that case, water is converting to steam without changing temperature. So in this portion, no change in temperature. No change in temperature. Okay, same thing will be true for that region. But here you see, in that plot, you see water. This means if you supply the heat, change of temperature. So here, no phase change. Okay, so this is just a plot that tells you how it looks like. Okay, let's do some problem here. So suppose you pour 0.25 kilogram of 20 degrees Celsius water into 0.5 kilogram aluminum pan of the stove with temperature of 150 degrees Celsius. Okay. Assuming, there are some assumptions in physics always, assume no heat transfer takes place to anything else. The pan is placed on an insulated pad, heat transfer to the air. Okay, it's very small. As this is the calorimetry problem. So our goal is to find what is the temperature when water and pan reach at thermal equilibrium. So you see that thermal equilibrium means at the same temperature. Okay, so let's see the sketch, how it looks like. Okay, so first we have bucket with water. So according to question, this says 0.25 kilogram water at 20 degrees Celsius. Okay, so this bucket is placed over the stove. So we put this bucket on the stove. Okay, this is the stove. So we put this pan over here. This is the same pan. Okay, this goes here. So this is 0.5 kilogram at 150 degrees Celsius. Okay, so this means this water could go here. So this means it is taken out. So this means it's taken out when temperature goes to 150 degrees Celsius. Okay, so here we'll see that at thermal equilibrium, final temperature is, say, we don't know that it is theta degree Celsius, but we can guess this theta degree is greater than 20 degrees Celsius, but it is less than 150 degrees Celsius. Okay, so we'll find heat gain and heat loss, because we know we have two formula. Q equals mc theta, or we can use ml. This is the equation to use. Okay, equations to use. So in this case, we don't have phase change, so we are just using these two equations. Okay, this only. So you see that initially the water has temperature of like 20 degrees Celsius, and the pan has temperature of 150 degrees Celsius. So what will happen that if you put water in this pan, in this bucket, it will gain the heat. So heat gained by water. Okay, so how much heat gained? According to this formula, mc delta theta 0.25. Okay, a specific heat capacity of water is 4200, and change in temperature, so final temperature is theta, initial temperature is started with 20. Okay, then the temperature of this pan will certainly go down. So heat lost by aluminum can. This is aluminum can. Okay, this is aluminum can. So just I want to make sure that this water is actually poured here, not the can. Everything is put over the stove. Okay, so heat lost by aluminum can, so we can write 0.5. A specific heat capacity of aluminum is, it will be given 900. Heat lost happens, so final temperature was 150, then the temperature at which it reached is theta. Okay, so in this case we use this equation. So now we know that there is no heat loss in any form, so heat gained must be equal to heat lost. So we can just put over everything here, 0.25, 4200, theta minus 20, and it will be 0.5, and it will go to 900, it will be 150 minus theta. So you have to do some algebra. After doing some algebra, your theta value will be 59.1 degrees Celsius. So this is your answer. Okay. So this principle, heat gain is called heat loss, is also called the principle of calorimetry. Principle of calorimetry. We also call it. Okay. Let's try the other problem over here. Okay. So the specific heat capacity of ice they give you. A specific heat capacity of water is also given. Latent heat of fusion of ice is given, and latent heat of evaporation is also given. So we want to find amount of water, amount of heat required to raise the temperature of 2 kilograms of ice ball from minus 3 degrees Celsius to 100 degrees Celsius steam. Okay, so let's start with ice. Okay, so we have ice at minus 3 degrees Celsius. I start with the sketch. If you supply heat Q1, you have to heat the ice. It will not instantly convert it to water. It converted to ice. It will not convert to water. It is still in ice. But temperature changes from minus 3 up to minus 2, minus 1, finally at 0. Okay. So there is no change of state. If we continue supply heat Q2, then this is the temperature, is called the melting point. If you continue supply heat Q2, what will happen? It will be converted to 0 degree water. So here is a phase change happens. If you supplying heat Q4, or sorry, next heat Q3, water temperature will increase 0 to 1, 2, 3, 4, 5, and finally up to 100 degrees Celsius. So temperature will be 100 degree, that is water. Okay. Then if you continue heating, what will happen? Continue heating Q4. If you supply Q4 heat, it will be at 100 degrees Celsius, but it will be in the steam, in the gaseous state. Okay. The other thing we need to find, we have to find how much total heat required. Okay. So we have to find total heat supplied. This will be Q, which is the sum of Q1 plus Q2 plus Q3 plus Q4. You have to find all the heat supplied. Okay. So equations to use. You know that equations to use. You have two equations for the heat. Q equals mc delta theta or delta T, and other is ml. So you know that this is for change of temperature, this is for change of state. So you have to use these two equations. Okay. Let's do one by one. So let's see how much heat is required to convert minus 3 degree ice to 0 degree ice. So this is change of state, sorry, change of temperature. So you are using this equation MC, change in temperature. So it will be 2 kilogram times a specific heat capacity of ice. So they give you 2010 joule per kilograms per Kelvin. Okay. Change of temperature. So final temperature is 0 degree minus initial temperature is minus 3 degrees Celsius. So you can calculate. So mass in kilogram, everything SI system. So your Q1 will be in joules, something joule. Okay. Let's find Q2. So ice, 0 degree ice to 0 degree water. So let's do Q2. Q2 will be, in this case, you can see that there is a change of state from solid to water. So we must have to use equation M times Cl. So we can use that. So Q2 will be ML 2 kilograms specific latent heat of fusion. They give you in the question is 335,123 joule per kilogram. So you can simplify, you can get something joule. Then here we use the equation Q equals ML. Okay. In the first case, in the previous case, here we use the equation Q equals MC, okay, delta theta or delta T, whatever. This. Now, let's go to Q3. Q3, you have change of temperature. So again, you can write 2 kilograms. Now it's water. So a specific heat of water is 4200 joule per kilograms per Kelvin. So temperature change, final temperature is 100 degrees Celsius, initial temperature is 0 degrees Celsius. So here we again use the equation M equals MC theta. Okay, MC delta T or delta theta. So you can find this was something joule. Finally, you can find Q4. Q4 is the it could go here from 100 degree water to 100 degree steam. So there's phase change. So we must have to use the equation Q equals ML. So a specific latent heat, but in the case of change of state from liquid to gas. Okay. So in this case, you can write it will be 2 kilograms, mass will not change, and a specific latent heat in this case is 226,10203040 joule per kilogram. Okay. So you can find this, then finally you can get the answer by adding all of these. So it will be Q1 plus Q2 plus Q3 plus Q4. Okay. So you can get finally this much amount of joule over here. So you can practice. Based on that, you can solve this problem. So in this case, this first part is the given informations. In second part, you can find the amount of heat required to raise the temperature of 2 kilogram ice ball from -3 to 100 degree steam, but be careful in this time, the ice is kept in a copper vessel. Okay. In first case, the problem I solved, here we ignore the vessel or container. But here we have also to consider the containing vessel. So the question looks like very similar, but you have to think about that. Okay. So you can solve this problem